Recall that this week we're talking about statistical tests. Check the previous videos for why we might want to do that. This video, however, is about statistical tests on discrete distributions. Remember, we talked about discrete versus continuous distributions in our math review. Check out links if you haven't seen the beginning of the class down below. Along the way, we'll introduce a concept of degrees of freedom, which we'll see more about in the next video on continuous hypothesis testing. Let's start with a very simple hypothesis test. We roll a die 36 times with the null hypothesis that it's a fair die. But 3 came up quite a bit, and 4 only came up twice. Is this actually a fair die? Remember that statistical tests are typically framed in terms of a null hypothesis. The null hypothesis here is that the die is fair. To measure how unlikely the null hypothesis is, we're going to need a distribution called the chi-squared distribution. This funny guy here is the letter chi in Greek. The chi-squared distribution has a parameter called the degrees of freedom. The chi-squared distribution is the sum of n draws from a standard normal, that is mean 0, standard variance of 1. Here's what the distribution looks like for several degrees of freedom. And here are the ugly formulas, which you won't have to use because you can just call the appropriate function in Python. Okay, keep the chi-squared distribution in mind, but first, let's go back to our die. What would you expect the results to look like under the null hypothesis? If the die were fair, every outcome would be equally likely. We would expect that each of the outcomes would have 6. Now it's time to discuss the test statistic for this kind of test. This is the first time we're seeing a test statistic, but we'll see it again and again and again. It's a single number that measures how close or far away we are from the null hypothesis. So for a discrete distribution, we take the difference between the observed cell, for example 8 for outcome 1 being on the die, the expected value in a cell, in our example 6 for every outcome, square that difference, and divide by the expected value. Under the null hypothesis, this test statistic is distributed as a chi-squared distribution with k minus 1 degrees of freedom, where k is the dimension of the discrete distribution. So let's take a look at that distribution with 5 degrees of freedom. The expected value of the distribution is 5. So 5.33 is not that far away. But what we care about is the probability of this happening. Recall the p-value is the probability of getting the test statistic or a more extreme test statistic. So we integrate under the PDF to the right to get 0.38, which isn't enough to reject the null hypothesis under the typical threshold of 0.05. This is a fairly simple example of using the chi-squared distribution to test a discrete distribution. Let's now ask whether 2 outcomes are independent of each other. While we have everyday definitions of what independent means, in statistics, independent means that the probability of x and y happening are equal to the product of the probabilities of x and y on their own. If the distribution of x depends on what y is, then they are not independent. The probability that it's raining is not independent of whether or not I have an umbrella. That's why it makes sense to look out your window, and if you can't tell whether it's raining, whether or not people have umbrellas might be a good clue. This doesn't tell us anything about the causation or why they're connected. But after you figure it out, it might be worth investigating further whether umbrellas cause rain. If you flip 2 coins, that's independent. But if you're pulling out of your dryer socks, then the color of the first sock is not independent of the color of the second sock, because drawing that first sock out reduced the population of your socks in the dryer. Deciding whether 2 things are independent isn't easy. We'll talk about a statistical test to do this in a second, but sometimes you need to think about this carefully. Deciding whether 2 things are independent is not easy. You might be tempted to try to use this using logic, but for example, take 2 die. You'll almost always see this example as a canonical example of what 2 independent distributions look like. But if you actually think about it, there's a force of gravity between the two. And the result of the first die will change the configuration of mass in the universe that will change how the second die rolls. But the question is, will this actually make a difference? Statistical tests of independence allow you to actually detect whether two distributions are independent or not. There are other crazy examples along these lines you can think of. Whether it's raining in the number of taxi licenses, it's also probably not technically independent because taxi drivers might take a day off to get their license if it's raining, but it probably doesn't make sense to model that. However, how long it takes to get a cab if it's raining definitely is not independent. And the first two words in a sentence are certainly not independent. If the first word is "and," then the second word isn't Russian. But there's a big question about what might technically be independent and what we can prove from data or models. So let's get back to hypothesis testing. We want to see if, when two words appear together, they are a collocation. Collocation are pairs of words that mean more than the constituent parts. Sometimes this reflects selectional preferences. For instance, you say strong tea, not powerful tea, even though strong and powerful are synonyms. Other times, they're just fixed phrases that go together, like intents and purposes or helter-skelter. Similarly, parts of place names are not independent. You almost never see Boca or Raton by themselves, but instead together as Boca Raton, a town in Florida. They're not independent. But you can't just look at which pairs of words appear together most. These are just the most frequent words in the language. They are independent, but with high probability for each word. So the probability of word 1 times the probability of word 2 are big, not because they appear together often, but because they are individually frequent. So we investigate them using something called contingency tables. You have one probability distribution as the columns, here word 1, and one probability distribution as the rows, here word 2. You count up each of the instances, and you get a total in each cell of the contingency table. Now's a good time to introduce a little bit more terminology: joint and marginal distributions. Joint distributions are distributions over multiple variables. So instead of just the probability of x, you have the probability of x and y and z and maybe a bunch of other stuff. Marginal distributions, on the other hand, are distributions over a single variable. They're called marginal distributions because to get a marginal distribution from a joint distribution, you sum or marginalize out the other variables in the joint probability function. For example, if we want the marginal distribution that the weather will be hot from this joint distribution over the probability of temperatures and weather, you need to sum over the probabilities that the temperature will be hot and sunny, hot and cloudy, in the first column of the table. And that gives us 0.15. And this is the complete marginal distribution. If we now want the marginal probability that the weather will be sunny, you first need to sum over the first row of all the possible temperatures. In this case, we get 0.4. Of course, the rules of probability still apply. Everything still needs to sum to 1, and you'll notice 0.4 plus 0.6 gives you 1. Okay, now back to our contingency table, not of probabilities, but of these counts. In the top left corner, we have the number of times we saw the phrase new companies. Top right is all pairs of words that end with companies but don't start with new. Bottom left is all the pairs of words that start with new, and bottom right is all the pairs of words that don't start with new and don't end with companies. The degrees of freedom here is 1 minus the number of rows times 1 minus the number of columns. So in this case, 1. This is because given one cell and the row and column totals, you can fill in the other cells. Let's now see if this joint distribution is independent. Just like in testing whether a die is fair, we need to compute the expected distribution if these were independent. To do that, we need to compute the observed marginal probabilities. For example, if the two were independent, the expected value of the top left cell would be the marginal probability of word 1 being new, 15,828 divided by 1.4 million times a marginal probability that word 2 is companies. 4,625 divided by 1.4 million. So we fill in the expected value table and see that the expected number of new companies is lower than what we observed, 5.17. As before, we compute the squared difference with the expected value from observed divided by the expected for each of the cells to get a value for the chi-squared test statistic. So top left cell, top right, bottom left, bottom right. This is 1.55, which is fairly far out along the tail. But the p-value is only 0.21, so we can't necessarily reject the null. As we're seeing, it's often hard to reject the null unless there's very clear evidence. We want to be conservative in rejecting the null, which is good. We'll now see how this changes for continuous distributions. If you want to see more videos like this, check the video description for the course that comes from the link down below. You can then see the context and the correct order for watching these videos. YouTube will gleefully show you stuff in the wrong order. If you want other people to see this video, provide a big gradient to the recommendation algorithm by clicking the like and subscribe button down below.